Hello and namaste. So from today onwards, we are deciding to launch a Zoom talk about some of the applied mathematical and computational uh, topics related to graduate, and most of them are graduate related, and some of them are undergrad related, and which are used in industry and many other fields. So this first talk is about Lagrange interpolation, which play a crucial role in engineering in some of the applied fields like physics and computer science. But basically, at this moment, in this scenario, it plays a vital role in computer science, in machine learning, particularly in and data science. So, to interpret and to explain about more detail, we have a graduate student from Florida Atlantic University, Mr. Deepak Bastola, and he is going to deliver a short introduction and a brief discussion about Lagrange interpolation polynomial. And let's welcome Deepak Bastola.
Thank you very much. Thank you, Mr. Acharya. Can you hear me okay?
Yeah, I'm fine.
All right. Today I'm going to talk about the Lagrange interpolation polynomial. Basically, Pitama already told about a little bit of this. This is very crucial and important in the field of the emerging field of data science and machine learning and artificial intelligence. Also, traditionally, it is actually being applied in the computational mathematical field, and it has a tremendous applications that are growing up. So we decided to talk about Lagrange interpolation polynomial. Usually the students in graduate level students, they do this kind of stuff. So we want to just make sure that the people who are really eager to explore the data science and machine learning, that this content would be much helpful for them to work for their field. So let me begin the content here. Today I will be talking on these areas of this particular topic. Firstly, I will introduce what is interpolation, and then basically the topic today is mainly concerned on polynomial interpolation. So we will be more discussion on this topic, and then what is the mathematical derivation of the particular polynomial interpolation. In specific, we will be discussing about the Lagrange polynomial interpolation. Also, we will do the numerical calculation with the mathematical, the expression. And also we do there, of course, there would be some error, right? So we will definitely be analyzing the error, what kind of error we will have, and how can we minimize those error in the large extent possible. And also, yeah, of course, we will conclude the talk. So let me begin with the definition of the interpolation. This actually, the interpolation is to estimate the unknown values within the range of known data points. So there we will be having some data points. They are known from our past observations, and we will definitely apply them to understand what would be the other unknown values, maybe in the future or maybe in between of the range of the observed data points, right? So when we have a set of discrete data points and want to find the value of function at a point, actually the point between these points, so the interpolation allows us to construct a new data point within the range of the known data. All right, so this is what interpolation is, and there are actually more than three kinds of interpolation, but I have listed here three major interpolation types. The first is, of course, the linear interpolation, which actually uses a straight line between two known points. And like for this formula, you can see that for a point x between x0 and x1, the interpolated value y can be found, right? Using this formula. So you can find the value y by applying this particular formula. This is just the equation of a straight line, and that will interpolate your functions or the unknown values that may occur within that straight line. All right. So the other kind of polynomial is, of course, the polynomial interpolation. This is, of course, our focus of the presentation today. We will be more discussing on it, and this will be actually determined applying this formula. The px equals to it looks very weird formula, right? So this is what we are going to discuss today. Um, And there is other interpolation as well, which also plays a very the vital role in the interpolating field. So this is a spline interpolation, which can be derived applying this formula below. How this works? This actually the divides the data into intervals and fits a low degree polynomial. The low degree polynomial means, of course, it's not a straight line. The line is not the linear interpolation. Also, it's not the quadratic. We usually often use the cubic, the polynomial. Actually, we do it in each interval, and this approach called also called the cubic spline interpolation, and it ensures a smooth curve and avoids oscillations, and also making it useful for approximating functions over large data sets. All right, so here in the formula you see the SIX is the cubic polynomial for the interval, let's say xi to xi plus 1. And these all AI, BI, CI, and DIs are the coefficient determined to satisfy the certain conditions. Okay, so yeah, this is what the spline interpolation is, but we are not going to discuss more about it. Maybe we will do it in the coming presentations. So the applications of the whole interpolation is growing, but not limited. But there are, the some places usually people are applying it more and more. This is one field of the application is engineering, like for the signal processing and so many things that people apply this interpolation. Also in data science and physics, right? Um, I can talk a little bit about how they are, applied in data science because people might be more interested to listen how they are applied in these fields. Like in data science and machine learning, we do data imputation, right? Sometimes we may not have the values; those are missing in our observations, and we want to impute those missing values with some reliable data in there, right? So for that case, we will be filling missing data to maintaining the continuity, right? On that continuous, the observed data, what is missing there? So we will input those missing values applying the interpolation. And also we resampling the data, like regularly resampling the time series data and so on. That what comes into play in data science, in machine learning, and time series, and even also in the regression and so many fields, right? So also I was talking in the engineering like signal processing. So like up sampling or down sampling kinds of things happen there. So changing signal sampling rates could be one of the field of application in engineering. Also, we want to do some kind of noise detection most of the times in engineering, like smoothing noisy signals, right? We do also do it in time series data set as well. And like in the computer graphics and image processing, also it has a tremendous applications. We be doing like image scaling, and for that we need to do the enlarging and syncing image smoothly, and also texture mapping, like the mapping textures in three-dimensional, the 3D graphics. Um, yeah, so also in other fields, in physics and even in a GIS, the geographical information system, we do the terrain modeling, we do the spatial analysis, that, like in estimating values at on major locations. These are all the field of applications of this interpolation. And of course, it is not limited. We can explore it more and more in like the finance and economics, like yield curve construction, stock price estimation. Even though we cannot do the stock price estimation accurately, but it is somehow helpful to estimate the stock price trends, right? So what is the trend of the stock price? So we could also, do some kind of interpolation on that. All right. So these are all the applications and a kind of interpolation. Now we will be focusing on why, how the interpolation, especially Lagrange interpolation, is defined and can be applied in the real field. Okay. So even before beginning, why it is important and like how it looks like, we first want to thanks to Westress for basically developing this theorem called Westress approximation theorem. He actually told to us like a polynomial is a good approximation for any continuous function, right? So we are basically interested in this particular talk here that a polynomial can be the right, the function that actually we could we could interpolate a function. So the Weierstrass derived and proved this theorem, saying that a polynomial, there exists a polynomial which actually interpolate any function, right? So if you are interested to see the proof of this, how the polynomial can be approximated for any continuous function, there are all real analysis, the courses that you can go through, like the Bartels or many writers have written a very good proof on it. Okay. So now, if a polynomial is helpful to interpolate a continuous function in certain interval, then there is a polynomial, a very popular polynomial, Taylor series, right? Taylor polynomial. So the Taylor theorems says that if there is a continuous function, so which is differentiable on an interval, and if the n plus 1 derivative exists on the given interval, then for every x values on that interval, there exists a number zeta x between x naught and x with fx equals to p n x plus r n x. Okay. So here the p n x is the polynomial and r n x is of course the error, is a random noise. Okay. Is remainder also sometimes people call. So here the p n x is a polynomial. Okay. And then r n x is the error. So like Taylor theorems tells us of function, right? Fx is exactly p n x plus r n x. So then here fx is now approximated, fx is now interpolated with p n x, the polynomial, with some random error, right? So Taylor series also looks like could be one polynomial interpolation. Okay, so we will see how the Taylor theorems or Taylor polynomial can approximate, can interpolate a function. But our focus is again Lagrange interpolation, not Taylor interpolation. And we will see why Taylor interpolation will have a more error than the Lagrange interpolation. And the Lagrange interpolation is, of course, better than the Taylor interpolation. All right. So let's give an example and interpolate it using the Taylor approximation. Here is a function. Say the function is 1 over 1 plus x squared. Okay. So we wanna approximate this function 1 over x squared in the interval minus 5 to 5, applying a Taylor polynomial. Okay, so the Taylor polynomial at 0, these are the polynomial. If you are approximating this function fx with second order Taylor polynomial, then it looks like 1 minus x squared centered at 0, right? So with the fourth degree polynomial, you could approximate with something here. You can see like 1 minus x squared plus x4 over 2. If you do it with the higher degree, if you go with degree 6, then you could approximate with the p6x is 1 minus x squared plus x4 to the x4 by 2 minus x to the 6 over 6. Okay, so like we are approximating 1 over 1 plus x squared, applying the Taylor polynomial with a different degree Taylor polynomial. Okay, if you notice here, the Taylor polynomials are almost accurate near x equals to 0, near to the center. But they are not accurate. They are more diverse if you go with the beyond the center, right? So, for example, if the fx gives you just 1 if you plug in x equals to 0 in the function fx, right? Here, if you plug in 0, then you get 1 over 1 plus 0, which is just 1 over 1, which is 1, right? So the fx is 1. And then also, if you apply the same thing at x equals to 0 at the center, then the second degree polynomial is 1 minus x squared, which also essentially becomes p2x equals to 1. So it's exactly the same. It is doing the better approximation. It is actually not even better. It's exactly same. The value it is giving. It has been actually been able to give return to it, right? So fx equals to 1, p2x equals to 1 for center at x equals to 0, right? So p4x, that also becomes 1. p6x, that also become 1. So like you see, at the center, Taylor polynomial is best polynomial to approximate the function. Okay, so you are getting exactly same value. But if you try to be further away from the origin, I mean the center, x equals to 0, if you apply not 0, 1, then what do you get? The original function becomes 1 over 2 is 0.5, but the second degree polynomial becomes 1 minus 1, which is 0. It's not same. You are getting 0.5 and you have you don't have exact value now. Is P2x is 0. Right? If you go for P4x, then what that becomes? It becomes 1 over 2, right? So if you just apply x equals to 1, then it becomes 1 minus 1 is just 0, and 1 over 2, just 1 over 2 is 0.5. So like fourth degree polynomial looks like accurate in case of 0.1. So if you go further away, you will have either more and more errors coming, right? So then if you go to the border of this interval -5 and 5, if you are near to those values, then if you are far away from center, means you will have a more error on this case, right? So this is how Taylor polynomial be working for approximating the function. We can see that visually using simple code here. I worked it in Python. Yeah, so the function is here 1 over 1 plus x squared. All right, I'm checking it in the interval -5 to 5. And my second degree is like this one, fourth degree, sixth degree, eighth degree, right? So if you go further away with a higher degree, you will see what happens. Okay, so once you run, right? So once you run this code, uh, it is quite interesting that we see like in the central, it will be more accurate, and out from beyond the center, it is not. See here. So this is a function. This is 1 over 1 plus x squared, right? That the black circle, the black color this graph is the first one, which is 1 over 1 plus x squared, the original function. And if you interpolate it using a Taylor a 2-degree polynomial, then it is something like this blue color. You see, that is that is that looks like this one. So at the center at x equals to 0, right? At this x equals to 0, this is exactly same. The original polynomial, original function, and my second degree polynomial, they are both the same. If you go with the P4 X, if you see that kind of orange color, then the dotted orange color, you see that is again accurate in the center, x equals to 0. But if you observe, everything after, the far away from center are not able to approximate my actual original function. See, my original function is like this shape, but all of my polynomial, Taylor polynomial, they are far away if you are approximating that far away from the center, right? So this looks like it works better in the central value, but it is not that a good approximate beyond the central value. If you go far away, they are not good to approximate the exact polynomial. All right.
I have a question.
Oh,
Just
please.
can you go to that slide?
You mean the code?
Yeah, yeah, previous. So
Yes.
this figure basically says that the data are concentrated on the center. That means at the point x equals 0.
Right.
So for the practical point of view in applied problems, so does this work, or there are any other ways to approximate this function?
Of course, this works. If you are more interested to see the observations near to your interest central value, right? Then it would be better approximation, right? The Taylor polynomial. But if your real world data points are like if you want to approximate the whole function, it may not be the better one because you see there are more error in the left and the right. Uh,
Right. So as we go on more and more values to the right and left to the value of x, I
mhm,
think there is more error. Error is
right.
increasing.
Yes.
So the value sounding of x equals 0. I think that's okay. Yeah, here in between -1 and +1,
Right,
it is
something like
accurate. Yeah, yeah, yeah.
negative
That's
1 to
good.
positive 1.
So
It is
if
more
you go
concentrated,
beyond
and
beyond that
all the
values,
polynomials are approximated accurately on -1 to 1, right? But
yeah,
if you go farther away from -1 to 1, then
yeah.
it is not being able to approximate my function.
Yeah, yeah, it is scattered, like scattered. So I think the error is increasing as we increase the value of x, right?
Of course,
Yeah, thank you.
that's true.
Got it.
Is that
Yeah.
all right? Okay, so then let me go to introduce the actual thing that we are interested to listen today. It's a Lagrange interpolation polynomial, right? So then we want to minimize the error because we just seen that there is error growing in, the error are maximizing right after the concentrated center. So how other, the polynomial could help us to minimize those error if we even go farther away from the center. This is the Lagrange interpolation polynomial that helps you to do the better approximation even though you are far away from the center. All right. So the Lagrange interpolation actually the unique polynomial of degree at most n that passes through n plus one distinct data points. And of course, this method is particularly useful for approximating functions based on a discrete set of values. And that ensures the polynomial matches the function at each of the given points. And the main contribution for this interpolating polynomial was by Joseph Louis Lagrange. All right. So we will see how this would work for the same function, right? We just seen that it is for 1 over 1 plus x squared, how it worked for my function to approximate by Taylor polynomial. Here we see in this particular, here is a code again, and then I applied here the Lagrange interpolation. I applied the formula, the formula that I have shown here before, this one, right? The px equals to something like, the very weird formula here. So we applied that formula here, and then we will see what happens with the same function. How is it like the better than Taylor's or not? Okay, so here we go. So now the black color function is again my original function, which is 1 over 1 plus x squared. And this dotted red circle, the dotted red curve is the Taylor P6. I particularly choose P6 from the Taylor. And then the Lagrange interpolation is this blue color one, right? So you would notice here my original function, the black color, this curve, is being more accurately, it's not accurate, but again, it is nearly approximating better than the Taylor polynomial because Taylor polynomial is just concentrated again with the center, but it is beyond the center. It is going, from my somewhere in the minus 4.7 to somewhere like 4.7. So it's like it is being able to dissimulate it. It is being able to just scatter to inside around my curve, right? So it looks like at least not that accurate again, but it is better than the Taylor. All right. So that made us, that motivated us to understand how this works and what is this actually. So here we will talk more about it. So the Lagrange theorem tells us if there are n nodes, okay, actually the n plus one distinct numbers, x naught to xn, and there is a function, okay, whose values are given at this number, and then the unique polynomial px of degree at most one exists. Who told us that exists? We talked about that in the previous slide. Wester told us there is a polynomial that exists and that can approximate the continuous function, right? So that's how we are developing this Lagrange theorem with the help of Wester's theorem, right? So we have a polynomial called Pxk here that can approximate with for our function fxk. And of course, there will be error. We will see that. So the polynomial now that is going to approximate our function is Px. This is a Lagrange polynomial. The whole this thing is Lagrange polynomial. This is just the formula that we had seen before, and this is what the Lagrange polynomial is. So this is how we are going to approximate applying this particular formula, and we will approximate our function fx with this Px. All right. So the terms here in the formula Lagrange interpolation, the fx naught, they are all these the evaluated values at for the function at x naught and x1 and up to xn, and this L and n is something derived with this formula. Okay. All right. So this formula works when your k value, right here, you must not be your, like if you see here, your xi should not be equals to k, otherwise you would get 0, right? So we just avoid those conditions, and then this is how we get L and K, and we find this L and K using this formula, and we just apply here, and we get polynomial Px, and that will be better approximation for the function fx. So this is what the Lagrange theorem is. All right. So now we will apply this theorem, right? This formula to approximate the function 1 over x. Is it better than Taylor? How it could be approximate my function fx, with the Lagrange interpolation. So this is a function fx equals to 1 over x, and I want to see it in the node x naught equals to 2, x1 equals to this value, x2 equals to 4, right? So now I want to see the second Lagrange interpolating polynomial for fx. Okay, and I will see what happens at f of 3. Will it be able to interpolate a value p3 near to 1 over 3, or how far it goes? Okay, we will be interested to see that. So f of 3 is 1 over 3, sure, but what happens p3? Okay, is that b going to be very close to 1 over 3, or it is far away from that? We will see it. So here we do it. So the second degree Lagrange polynomial is P2x, which is just using the formula, we get this thing, right? So now each L net x, L1x, and L2x are being calculated, and they are like this. They are again the function, different looks like this. And then if you do it for P2x, right, if you just plug in these all things here in my formula, in my theorem, Lagrange theorem, then you get this polynomial 1 over 22x squared, 35 over 88x, and 49 over 44, right? My original function is 1 over x, and my second degree Lagrange polynomial is p2x, which is this. So now I'm interested to see, oh, is it the approximating polynomial for 1 over x? All right, so we will see that. Okay, so this is a polynomial of second degree that we just got. This is a Lagrange polynomial, right? So we will see if this is approximately fine to interpolate my original function f equals to 1 over x. And here we are also interested to see what happens at x equals to 3, right? So in the particularly, what happens to p2x when your x is 3? So of course, the function value f of 3 that we already seen is 1 over 3, which is approximately 0.33. And if you apply p to 3, just in this polynomial here, if you just plug in x equals to 3 here, then we get 0.3295. It's a good news. See, this is approximately the same. The first degree is exactly, first decimal value is exactly same, and it is somehow not, but it's 295, is 333. So it's like close, right? So we are closely approximating the value in the function applying this polynomial. Right? So of course, this is a close approximation to the actual value. All right? So we will see that how it looks in the whole range. All right? Hmm. Okay, over here. So I'm applying this code for 1 over x for the function 1 over x in the range 2. Nords are 2, 2.75, and 4. These are my 3 nords, and I'm going to see the whole the graph, what happens. All right. So Lagrange approximating 1 over x, this black color curve is again my 1 over x function, and this Lagrange interpolating polynomial is this blue dotted curve that looks like pretty good. Say the my original function, the black color graph, is now nearly interpolated with this the blue color dotted. They are very, very, very near, from all the way from 1.5 to 4.5. They are pretty much close to the original function. Right. So, and if you see like actual value f of 3 is 0.33, right? At 3, it is like 0, the red color one. If you see that, if I can zoom it out, oh shit. Okay, if you see that at this point, this red color and kind of this dark red color and the green color are closely together, right? So that's how we had approximated actual value f of 3 in the function by the polynomial p3. All right. So this is about the approximating of the function using the Lagrange polynomial. So we will be discussing a little bit about the error. Still, you see, if you observe here, you still have a error, right? It's not exactly same. It's not the exact same thing. It's some it's close, but it's not the exact, right? So we have some error on that, right? So Lagrange is also not the exact thing that can do for the function, but it is somehow closely approximate the function. So we have that error, and what that error is, we have seen that in the formula before. The error part is R and X, right? This reminder is also in the Taylor theorem, and in this case, also the R and X. This is the error that we will be discussing about here. So this is what the original function is, right? And this is a polynomial, so Lagrange polynomial. So the difference is, of course, the error. It's if it is zero, of course they are same, but there it is not zero. We have some RNX, right? We have some remainder. We have some errors. So this error will be calculated by this formula. So this is the error for the Lagrange interpolation polynomial, and we will see that this of course the error depends on this n plus 1 degree of the differentiation. If it is small, if this value is small, then error is small, right? So we of course see that with the second degree, I mean the maximization and minimization applying the calculus things, right? So we will check the second order derivative and see and try to minimize this error applying the calculus here. Yeah, I will not discuss it more on this talk today, but you can minimize this thing at the numerator to minimize your whole error. And also it depends upon the product of this x and xi minus 1, right? So this error bound, if this increases, of course, our this what's called this error will increase in that case, right? So in the interpolated nodes, if they are far away, of course, this error will increase. All right. So now, how other methods could be applied to minimize those errors, right? So if we closely observe here, then my errors is also depends on the distance between my nodes, right? So here in the Lagrange polynomial, I assume the nodes are in the equal distance. Okay, the x naught, x1, x, like you see in the picture here, it's like 1.5 and 2 and 2.5 and 3 and 3. So all my nodes are in the equal distance. But if I am somehow would manage my nodes to be in not in the same distance, but in some other way, then that could minimize my error. Okay. And thanks to Chebyshев, okay, there is other methods. Okay. So we could apply that Chebyshef nodes to actually ideally place my nodes to minimize my error. Okay, so this is a Chebyshef formula, and this xi in nodes, and by this formula, we can place our nodes so that our error gets minimum. All right, so how does this work? So if you apply that Chebyshef to the first one, okay, the first example that we have seen, 1 over 1 plus x squared, and if you apply the Lagrange polynomial with Chebyshef's nodes, then how does it look like? It is, of course, be better than the simple Lagrange polynomial nodes in the equal distance node. If you apply that, see here. So if you go and see that again before, your Lagrange polynomial with this blue color function, this curve, was a little bit farther. It was, of course, better than Taylor, but it is still because of this equal distance node, -4, -2, and 0, and 2, 4, 6, right? So the equal distance nodes, there were equal distance nodes here, and that was not the better approximation. But with that Lagrange interpolation polynomial, if you apply Chebyshef nodes, then in that case, you would see this thing is happening here. So it is more accurate than that one, right? So you are better approximating the function. So this is what Chebyshef nodes helps for the better approximation for the Lagrange interpolation. So you apply Lagrange interpolation, but with Chebyshef nodes sounds better. Okay. All right. Then of course, this is now going to be end of my talk today. So what we've seen with the Lagrange interpolation polynomial is actually better than Taylor, because Taylor just approximate in the central value, but it is better in across the the in interval. And also the flexible knots, actually you could make the flexible knots, right? You could make the knots not to be in the equal distance, to just minimize the error and avoid the oscillation. You can just go with the Chebyshev, and you could fix the knots using the Chebyshev formula. And of course, this is higher precision. It could provide the higher accuracy than the linear interpolation and the fitting polynomial to the multiple points, right? And also, of course, there is a more better interpolation. The spline interpolation cubic polynomials could be better than Lagrange interpolation. Our today's talk is, of course, the Lagrange interpolation, and we see that how the Lagrange interpolation could be applied, and it could be, interpolate my function. These were my references of the talk. And yeah, you can go through these books and the proofs and the things that you can explore more about it. Thank you. So this is the end of my presentation. If you have any questions, feel free to ask them. I enjoy answering the question. Over to you.
Thank you. So, can you go to the slide regarding subversive notes?
Sure.
Um,
Is right?
yeah. So, uh, this is uh, uh, this is a method of correcting the what means like are there drawbacks of interpolation regarding Lagrange, and this is the better technique rather than Lagrange interpolation, or it is something else?
It is actually a technique that could fix where to place your nodes, right? So before you see in simply in Lagrange interpolation, you see your nodes are in the equal distance. So Lagrange interpolation basically assumes nodes are in the equal distance. You just make the partition of your intervals. If you are from like -5 to 5, then you partition that into 500 equal, the nodes, or you can do it for the any height of the interval. All right. So
Mhm.
this is how the basic Lagrange interpolation assume about. But if we apply that equal distance, means you are getting the higher error here. But the Chebyshev is actually applied not to fix your knots in the equal distance, but with this formula, you will be able to fix your knots so that you would get the less error. And they may be in equal distance, they may be not in equal distance, right? So it has the flexibility. It gives you the flexibility to find the knots. So to answer your question, this Chebyshev knots is actually to fix the knots in the Lagrange interpolation. This is a kind of making more accurate for the Lagrange interpolation, applying the other way to the knots.
Cool, got it.
Did that answer your question?
Yeah, yeah, that's just to minimize the error.
Right. Because we see, if you want to go further, because you see um, in the formula here, if you see like this x minus xi is the distance from your x value to the node, right? Your
Mhm.
xi, these all xi are the nodes. And how you are define this x and minus xi? Your I is just xi equals to 0 and then 1 and 2. So like this is something that you could minimize to minimize your error, right? There are two ways that you can minimize your Lagrange polynomial error. The one way is with minimizing this n plus 1, the derivative, right?
Mhm.
The value of n plus 1 derivative. If you could minimize this, then of course you could minimize your error. Another way is to minimize this, the way of the product of this. The product of this x minus xi could be minimum so that your whole error would be minimum. So to minimize this, we don't have anything that we could apply in the Lagrange interpolation, but we are interested to minimize this product, right? So I discussed a little bit about how could you minimize it. You would see the function, you applied your calculus, the calculus, and then you do the second order derivative, you find the minimum and the maximum things from them, right? So you could apply some critical numbers there, and then you could see there is the absolute minimum things that is happening. So you could do that on it. There is nothing to do with these things applying the Chebyshev. But Chebyshev is helping the other way that you could minimize your error. And that was minimizing this product. And this is possible with this formula. You could apply this xi, and you find xi from applying this formula. This a and b is, of course, the in value of your interval. And with the period, this cosine function, you just apply this formula, and you see your xi will not will be something different than you get it from the Lagrange interpolation, right? And this is other way that you could minimize your whole error. So that's how Chebyshev helps us to minimize the error at the end.
Yeah, yeah, got it. So thank you very much. To wrap up, uh, yeah, Mr. Deepak Bastala, uh, he gave insight of the interpolation basically on Lagrange interpolation formula. So, uh, interpolation is a method which is used to estimate or predict the values that fall between the known data points. So, think of like filling the gaps in the data based on the information you have already. So, thank you for your presentation, and we'll come to the better topics next time. Thank you very much.
Thank you
Have a
indeed
good
for listening. Thank you everyone for listening today. All right. Have a good day.
day.